Multivariable Calculus, Section 13.4, Double Integrals in Polar Form. And here's one of my favorite little cartoons showing you where pi comes from. And as you know, we use pi a lot when we're in polar form. Volume above a polar rectangle. Now, a polar rectangle isn't really a rectangle at all. Here's a picture from your text. We have a surface defined by z equals a function in x and y, floating above what we call a polar rectangle. But the polar rectangle is actually made out of two curves and two line segments. So now we're going to be developing volume using this idea of a polar rectangle. The pink area there is a polar rectangle, and we have a radius from the origin out to the bigger curve. We have a change in the angle, and we have a change in the radius, and then the area in that rectangle, fake polar rectangle, is the change in the area, because what we're going to do is we're going to combine a lot of these. This is just one individual one. And then the arc length there is part of the circumference. It'll be delta theta out of the entire circle, which would be 2 pi, times the circumference. And then the circumference is 2 pi r. Notice the 2 pi cancels. And so we're going to pretend this is a rectangle and have the area be length times width. So it comes out to r delta theta times the change in r. And then as delta r and delta theta go to instantaneous changes, the area will become exact. So now here's another picture from your book. What we're going to do is combine a whole lot of these little delta areas to make the entire area and then multiply by the height. So we could sum the products of the heights times the areas, and we can substitute for delta A, r, delta theta. And so to get the area, we have actually 3 numbers there. And of course that morphs into the integral over the region, where we're taking every single z value, every f value, times the instantaneous r, every r value, and the instantaneous changes in r and theta. So this is our handy dandy formula. So let's look at this a little more closely, because x and y can't be in an integral that's in terms of r and theta. So if you'll remember, x is r cosine theta and y is r sine theta. So we're going to substitute those quantities for x and y. And then we change to an iterated integral, where we have limits for r, r1 to r2, and limits for theta, alpha to beta. Now here's another picture from your book. This integral only works if your region that your surface is floating above in the xy plane is radially simple, meaning that if you take a radius from the origin, it always passes neatly from the inner curve to the outer curve. So there we have some other radiuses. This region is radially simple and can be divided into little polar rectangles. And here's another picture from your text showing that first we integrate with respect to r from the inner curve to the outer curve, and then secondly we integrate from the smaller angle to the bigger angle. So we can't switch the dr into the d theta like we did with dx and dy. They have to stay in that order. So here's an example of using polar integrals. Find the volume of the solid bounded below by the xy plane and above by the paraboloid z equals 25 minus x squared minus y squared. So here's a picture, and as you can see, it would be convenient to use polar coordinates for that circle, because it is sort of a polar area. The radius is going to go from 0 to 5 out from the origin out to the circle. And then to get the entire circular region, the angle would have to go from 0 to 2 pi. And there is the rest of our formula, the z value times the area of the polar rectangle r dr d theta. So we're going to substitute r cosine theta and r sine theta in our z formula. So we get 25 minus r squared cosine squared minus r squared sine squared. And then we're going to distribute that extra r and factor out the r cubed. And that gives us our handy dandy, very familiar identity. Cosine squared plus sine squared just goes to 1. And so then we can integrate with respect to r. And the 25r goes to 25 halves r squared. The r cubed goes to 1/4 r to the 4th. And that has to be evaluated from 0 to 5. That gives us 625 fourths. Now we have an easy integral in theta. The antiderivative is 625 fourths theta, evaluated from 0 to 2 pi, which turns out to be 625 pi over 2. Volume above region bounded by two polar curves. So let's say our region has two boundaries, not just one curve, but two. So we've got this blue curve and we've got the purple curve. The outer curve is the purple one. We'll call that R2. And the inner curve is R1. We're going to have to let R go from R1 to R2, and then again theta will go from alpha to beta. So it's really the same thing, except you're going to have functions as your limits instead of numbers. Here's an example using double integrals to compute area. Here we have an inner curve, r equals 1, and an outer curve, r equals 2 plus cosine theta. And here's our formula for volume. Now remember, if we want area, what do? Well, we make the height of our volume 1. So the height's going to be 1. If the height's 1, the function value is 1, then the area and the volume will be the same numerically. And notice that r has to go from the inner curve to the outer curve, from 1 to 2 plus cosine theta, and then to get the entire graph, both of these curves are drawn once if theta goes from 0 to 2 pi. So now we take the antiderivative of r with respect to r and plug in our limits of integration, and the 0 part just goes to 0. And now we could multiply that out and use an identity, but that's a lot of work and you already know how to do that. So blah, 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 blah. I took out my calculator and then divided by pi to get the exact answer of 7/2 pi. So feel free to do these integrals on your calculator. Oh, who's this? Oh, I wanted to tell you something. This is sort of like a side trip. I was reading the book, and during the reading of the proof of the integral, they use double integrals to evaluate the integral of e to the negative x squared, which I always thought you could only do with a series. And so in the middle of that, there was a surprise, a step that I didn't understand. So I had to play with it, and I came up with something I didn't know before. So here's a little video of what I learned. So let's say we have a double integral whose integrand is the product of an expression in only x times a second factor exclusively in terms of y. Evidently, we can rearrange everything, including the integral signs. And end up with the product of two single variable integrals. Why this works is easy to see if we look at a simple example. Let's start by integrating the usual way. The antiderivative of y with respect to y is 1/2 y squared, which is then treated as a constant times the antiderivative of x squared. Now let's rewrite the double integral as two separate single variable integrals. Integrating the first one gives us 1/3 x cubed, and the second one gives us 1/2 y squared. Notice that in both methods, each factor is integrated without affecting the other factor. So what is the surprise? Well, the surprise to me was that you could take a double integral if the integrand was a product of a function in y times a function in x. You could take that double integral and split it into two single variable integrals and get the same answer. I don't know if that'll ever be useful, but I thought it was interesting. So let's jump in and do some problems. Number 4, use a double integral to compute the area bounded by one loop of the polar curve r equals 2 cosine 2 theta. So here's a picture of 2 cosine 2 theta, and there's the loop that I chose to evaluate. So here's our handy dandy formula. Notice that r is going to move from 0 out to the curve. And so r is going to go from 0 to 2 cosine 2 theta, and pretty obviously theta is going to go from negative pi over 4 to pi over 4 because 2 cosine 2 theta will be 0 at those angles. So that's my start and stop. So we integrate r dr and get 1/2 r squared, and we plug in our limits of integration, and we're subtracting 0. So basically all we're doing is substituting 2 cosine 2 theta for r. And we need to rewrite that using an identity, and then it becomes fairly easy to integrate. 1 goes to theta, and cosine goes to 1/4 sine 4 theta. And then we merely plug in our angles. Notice that sine of 4 times plus or minus pi over 4 is just 0. So basically all we're doing is plugging those values into theta. So we get pi over 4 minus negative pi over 4, which equals pi over 2. Number 10, use a double integral in polar form to compute the volume of the solid that lies below z equals x squared plus y squared and above the xy plane region enclosed by r equal to cosine theta. So here's a picture of 2 cosine theta. It's actually a circle centered at 1 with radius 1, and we shade in the region we're talking about. Notice that it is radially simple. Here's our formula. And now z is x squared plus y squared. So what is that in terms of r? Well, I hope you said r squared. And then we have the rest of our integral. R is going to move from 0 out to the curve 2 cosine theta. And this curve is entirely drawn from 0 to pi. So you have to be a little bit careful about those theta limits. They're not always 0 to 2 pi. If you went 0 to 2 pi, you'd get double the answer. Okay, and then we also have our r dr d theta. So that simplifies to r cubed, the antiderivative of which is 1/4 r to the 4th. Substituting 2 cosine theta and 0, we get 4 cosine to the 4th theta. And that would necessitate a bunch of identities. So instead, I just said blah, blah, blah and grabbed my calculator. And I got approximately 4.71238898. Number 16, evaluate by converting to polar form the double integral shown here. Now remember that dy dx is the area of an actual rectangle, and it morphs into r dr d theta in polar form. And then we have to convert x squared and everything else. So let's take a look at the region. Y equal 1 is the top function there, and y equal x is the bottom function. So if we graph those, we have to figure out, well, where is the area? Well, if we're moving from x up to 1 for our y value, and then from 0 to 1 along the x-axis, this has to be our area. So you see we're moving from the line x up to y equal 1, and then after we integrate that way, we integrate with respect to x from 0 to 1. Notice also that this area is radially simple because we can move from 0 along a radius to the line y equal 1. So here's our new integral. Notice that x squared morphs into r squared cosine squared theta because x is r cosine. And r dr d theta is replacing dy dx, And now we still have an issue with y equals 1. We need to change that into a polar function. So we'll go over here and we've got y equal 1, and y, you'll recall, is r sine theta. And so if we solve for r, we get 1 over sine or cosecant theta. So we're going to replace y equal 1 with cosecant theta. Now we're rewriting our integrand as r cubed cosine squared theta drd theta. And integrating with respect to r cubed gives us 1/4 r to the 4th. We keep the cosine squared theta and we replace r to the 4th with cosecant to the 4th, which is 1 over sine to the 4th. So to simplify that, we can actually group one of the sine squareds with cosine squared and get cotangent, and then take the other sine squared and make that cosecant squared. Now, there are various ways to do this, but I let u equal cotangent theta in my head, and that made the tag for the baby for cotan theta is negative cosecant squared. So all I need is a negative, and the cosecant squared goes away, and I've got 1/3 cotangent cubed theta. And of course I keep the 1/4 in the front, and I keep my limits of integration, and then I just plug those in, and I get negative 1/12 times the cotangent at pi over 2 is 0, so that's 0 cubed, and the cotangent of pi over 4 is 1, so that's 1 cubed, and we end up with 1/12 for our answer. Number 20. Use a double polar integral to find the volume of the solid bounded above and below by the following surfaces: z equal 2 plus x and z equal 4 plus 2x. That lies directly above the region of the xy plane bounded by r equal 2. Now, can you tell which surface is further up? We're talking about positive values here, so pretty obviously 4 plus 2x is the top surface, and 2 plus 5 is the lower surface. So we're going to subtract the lower surface from the upper surface, and this is still in terms of x and y. We'll change it later. And so here's our integral. And we have a polar region below. We could do this in x and y, but it might be a little trickier. There's r equal 2, so that's our region, and it's radially simple. So now our integral in polar form, dx dy changes into r drd theta, x changes into r cosine theta. R is going to go from 0 from the origin out to 2, and to get the whole circle, theta has to go from 0 to 2 pi. So there we have x changing into r cosine theta, and dx dy again changing into r drd theta. So now I distribute the r, and I get r squared cosine theta plus 2r, and we're going to integrate with respect to r. So the cosine theta remains as though it were constant. We've got 1/3 r cubed, and then plus r squared. And that has to be evaluated from 0 to 2. I didn't show the work for that, but I think you can figure that out. And now we integrate with respect to theta, and we get 8/3 sine theta plus 4 theta evaluated from 0 to 2 pi. And at 0, both those terms are going to be 0, and at 2 pi, sine is 0, so all we really get is 4 times 2 pi minus 4 times 0, and we get 8 pi. And now I leave you with an interesting surface. This is a two-dimensional representation of a three-dimensional representation of a four-dimensional cube known as a tesseract. So this is representing a tesseract or a four-dimensional, they call it a hypercube. Enjoy and have fun with these problems.